Alright, for finding probability, this was part of the last lesson that we had. So to find the probability, we find out how many times something happened, and then we would divide it by the amount of attempts. So that's how we'll be able to find these. Particularly, these would be experimental probabilities. For the horse race experiment, you will need 2 dice, which we have. For each roll of the dice, record the sum in the appropriate column below by shading in the box, which we will do. For example, a roll of 2 and 5 means you will shade one box in the 7 column. A roll of 1 and 4 means we'll shade in the box in a 5 column, because we're adding the 2 together. That's why it said the sum. Do this 30 times before you start. Predict which horse will win. All right, so let's take some guesses. What horse do you guys think will win? All right, those are some good guesses right there. You could have guessed whatever you wanted, but we're going to figure out which horse has the higher likeliness of winning. And by the way, whoever said 1, you can't actually roll a 1 because we're adding the 2 together. So I'm going to take my dice right here, which are a beautiful red color, and I'm going to roll both of them. Bam! I got a 2 and a 1, which gives us a 3. So I'm just going to shade in the box right here. Now this experiment says we're going to do it exactly 30 times. So we need someone else to come roll this for us, and then we'll fill in the boxes as we go. So looking at this, which horse won or had the most rolls in the group, we can see that 5, 7, and 8 all tied. And up here, we had estimations of 5, 7, and 8 would win. All right, now there's a reason why these 3 particular ones should win, even though it's highly unusual to get this small amount of 6s, and we'll see why here in just a moment. But we need to determine the experimental probabilities for these outcomes. So what we did on this is an experimental, because we actually threw the dice, and then we added these up to make an experimental probability. That's why these are considered experimental probabilities. And now we will find each of them. So 2, we had 1, 2 out of 30 total rolls. Right account. The 3s, there was 2 3s out of 30 rolls. And for 4, there was also 2 out of 30 rolls. 5s, however, had 5 5s out of 30 rolls. 6, 1 out of 30, and we'll fill in the rest. So these are the experimental probabilities for all 12 of these numbers. I guess 11. Yeah. So, with this in mind now, I think we'll figure out the theoreticals. Let's find out. All right, this says to create a class histogram that combines the data from all the group's histograms. We're just going to use ours. So a histogram is where we make these. Our x-axis, and then right here, this is our y-axis. We just got to label this garbage. So the histogram right here would look something like these. And then we just kind of outline the values that we got along the way. Like these. And we can see how this data has been distributed. There's been very few 6s and 2s, no 12s, but we got high values for 5, 7, and 8. So the question is, do you think that this game is fair?
No.
Well, we got to figure out what fair means first. What does fair mean? Fair games. That means that all the results or outcomes are equally likely to happen. Do you guys think that all the outcomes or results are equally likely to happen?
No.
No. So yeah, we would say this one is not. Specifically because in the experiment, we got different values. In fact, we got a 0 for the 12s. So probably not quite a fair game there. So in the experiment, we had a different number of outcomes for the outcomes. For example, we got 5. We rolled 5, 7, and 8 5 times each. A different number of outcomes for those 3 outcomes. Those 3 were the same, but the others were different, I should say. All right, what are all the possible outcomes when you roll 2 dice? We'll not work on this in a group. We'll just work on this one together. All right, so I'm going to do this the old-fashioned way, even though we have more formal ways to do it in mathematics. So we're just going to make a list. For example, one possibility is if I rolled a 1, then on the other dice I would get a 1. If I rolled a 1 on the first dice, I could get a 2 on the second one. If I rolled a 1 on the first one, I could get a 3 on the second one. Now these are just the outcomes. We got to figure out what the actual sum of these would be if I rolled these. So these are, in red is the actual outcome after rolling that pair. So we can see how many total outcomes do we have, Radhika? So we're going to use this. We're going to say, what are all the possible outcomes when you roll 2 dice? You could get a 2. You could get a 3, a 4, a 5. All right, you could get one of these possibilities. So how many total outcomes did we get?
36.
Yeah, there's 6 for each row and 6 rows. So there's 36 total outcomes. So now what we want is the probability of each of these. Well, what's the probability of 1? I don't see any 1s in that, so we'll say 0 out of 36 possible outcomes. What about the probability of 2? How many 2s are in this list? 1. There's 1 2 out of 36. How many 3s are there? 2 3s out of 36. How many 4s? 3 out of the 36. 5? 4 out of the 36. 6? 5 out of the 36. 7s? 6 out of 36s. 8s? 5 out of a 36. 9er? 4 out of a 36. All right, what about old 10? 3 out of 36. 11. 2 out of 36. And 12. 1 out of a 36. How do you think the individual probabilities relate to the probabilities of the sums? For example, the probability of 1 in 6 was 1 in 36. But the probability of 7 was 1 of 6, which was just the reduced form of our 6 out of 36. Why? Why is that true? All right, so in this table, yes, as you can see, there are many more ways to get a 7 than there is, for example, to get something like an 8. There's so many more. Or there's more ways to get a 1. No, not a 1. Like a 2 than there is to get a 12. Or they're the same. Or there's a lot more 5s on this because there's a lot more ways to get a 5 than there is, for example, to get an 11. Right there, right?